All right, the last section here is section 9, energy in chemical reactions. And this will be the end of chapter 7, which means that you'll have another test due after this, which will cover chapters 6 and 7. So make sure you're studying for that very well. But what we have here with energy in chemical reactions is very basic. We're not going to do any of the math behind any of this stuff, which is nice for you. But just understanding that energy does play a role in chemical reactions. For example, some reactions work better at cold temperatures than they do at hot temperatures, and some reactions work better at hot temperatures than they do at cold temperatures. But all reactions work faster at the higher temperatures. That doesn't mean it works better, because you might have a reaction where you would expect to get 80% yield, meaning 80% of the reactants actually go to the product that you expect. 20% would go to other things or are left unreacted. And if you do it at a higher temperature, you might get the reaction to finish, in a sense, earlier, but you might only get 55% yield. It might stay at 55% yield no matter how long you wait. It'll get to that quick, but it will stay there no matter how long you wait. So energy is a tricky component to all these reactions, but here's the basics. So every reaction has an activation energy. And activation energy is the amount of energy required in kilojoules per mole of reactants to allow a reaction to occur under specified conditions, meaning like temperature and pressure, concentration, so on and so forth. There is always an input of energy in all chemical reactions, therefore. They must overcome this activation barrier even if the product or products are lower in energy than the reactant or reactants. So what we'll see on the next page is how this actually looks if we graph energy versus, amount of heat added. You'll see what this activation energy looks like, but it's always higher than both the product and the reactant in energy. So we have two types of reactions based on energy. There's three, but two that are in this book. There's exothermic reactions, and these are reactions that release heat or energy to the surroundings. The chemical system has lost heat, lost energy, therefore. So the product chemicals are always going to be lower in energy than the reactants, and therefore the system has lost energy. Exo, meaning to exit. It's going out of. Whereas endo, meaning to go inside, like we have an endoskeleton, our bones are inside of us, but insects have an exoskeleton because it's on their outside. So endothermic reactions are chemical reactions that absorb heat or energy from the surroundings. They take them into themselves. The product chemicals, therefore, are always higher in energy than the reactants. Therefore, the system has actually gained energy. You can experience exothermic reactions. Well, a common one would be a fire. You feel that heat being given off, and you can feel it from a good distance away. What you don't realize is that the actual stuff reacting is actually getting lower in energy. It's giving it to us. In the converse sense, endothermic reactions are taking energy out of the system and giving it to themselves. So the reaction or the reacting system is actually gaining energy. You would be part of the surroundings experiencing this endothermic reaction and would be giving energy to it. Therefore, you would be lowering yourself in energy, which is why if you feel an endothermic reaction, you'll feel it as coldness. Examples of endothermic reactions would be like a cold pack. One from a first aid kit where you have to actually break an inner pouch inside of the larger pouch. When you do that, the chemicals inside the inner pouch react with stuff outside of it, and they react endothermically. And it gets cold because it's sucking heat into it in order to make it go. This is what they both look like, and you can see we have energy on the y-axis in both cases, and we have the progress of the reaction, or how much heat has been added, on the x-axis. It could also be time, if you want, progress of reaction. But if you look carefully at both, the exothermic reaction has products over here that are lower in energy than the reactants, but even when this is the case, you have this activation energy that the system has to overcome. So if there's not enough energy, say you have an exothermic reaction and you cool it down to, let's say, 70 Kelvin, which is extremely, extremely cold, like negative 200 degrees Celsius, around there. If you do that, the system is not going to have enough energy to go over this hill. And so it's just going to, the chemicals will roll back down. Imagine it being like a ball. If you were to roll a ball up a hill, but you only give it enough force to get to here, that ball's going to roll back down and stay over there. Same thing with these molecules, compounds, or atoms, elements. If they have enough energy, they'll go up, and then they'll go down to the products. Okay? And for an endothermic reaction, the activation energy is actually still higher than the products. So you have to put in more energy than is in some ways necessary in order to get there. This would be very hard to do. But you can see here why exothermic reactions are giving off heat, because the system is actually lowering itself in energy. Endothermic reactions take in heat because they're actually going up in energy. If this is the starting energy, it has to go up to here. And there's a whole lot of mathematics behind all this, and we could talk about that, but that's not for the scope of your class, so we'll just leave it as this. And the last slide for this lecture is on catalysts. Catalysts are any reagent present in a reacting system that allow the reaction to occur more quickly if all other conditions are being kept constant, like temperature, pressure, concentration, whatever. It does so, or they do so, by lowering the activation energy of the reaction, and they are not consumed during the reaction. This is why they call them catalysts. Not only do they make it quicker, but they're always there, so it doesn't even matter how much you add to it. You can add a sprinkle of a catalyst to a reaction, and it will just go like that. For example, hydrogen peroxide, you can have it sit out in a cup in your room, and it will decompose over time due to heat, due to light, but it's going to do it very slowly. If you add just a pinch of potassium iodide, though, it will spontaneously decompose and be completed within seconds. And just a pinch of it, whether you add a ton of it or a pinch, just the tiniest little bit will make it go. And it will go uncontrollably until all of the hydrogen peroxide is done reacting. So if we look at the energy diagram here, you can see as energy increases versus the progress of the reaction, the green curve, the green graph, is the original uncatalyzed reaction, whereas the purple one is the catalyzed one. And so you can easily see that the amount of energy required to get the reaction to occur has lowered by that much energy. And so that actually means that more atoms, molecules, or formula units of ionic compounds have enough energy to actually react and cause products. So at any temperature, the reaction will go more quickly. And catalysts do this by kind of acting as like mediators. They will bring the two reacting things together and say, here, you two come together and react. Whereas it might be more challenging for the two things to actually bump into each other in space normally. So that's one way that they increase the speed of the reaction or lower the activation energy. And that is it for chapter 7.